Introduction to ANSYS Fluent, Lecture 7, Turbulence. The theme of this lecture is that the majority of engineering flows are turbulent, and so therefore successfully simulating these flows requires us to understand a few basic concepts of turbulence theory and modeling. This allows us to make the best choice from the available turbulence models and near-wall options for any given problem. In this lecture, you will learn basic turbulent flow theory and turbulence modeling theory, the turbulence models and near-wall options that are available in Fluent, how to choose an appropriate turbulence model for a given problem, and how to specify turbulence boundary conditions for inlets. The objective of this lecture is for you to understand the challenges that are inherent in turbulent flow simulation and to be able to identify the most suitable model and near-wall treatment for a given problem. The famous dye streak experiment of Osborne-Reynolds is a good starting point for a discussion of turbulent flow. What Reynolds did was inject dye into liquid that was flowing through a pipe. If the velocity was low, then the dye trace would be undisturbed, which we see in the upper picture here. This condition is known as laminar flow. As the velocity of the liquid was increased, the dye would indicate that instabilities developed in the flow and irregular oscillatory motion resulted. This condition is known as transitional flow. Finally, as the velocity is further increased, turbulence would develop in the flow and the dye would become completely dispersed by the chaotic fluid motion. This condition is known as turbulent flow. Now, the velocity itself is not sufficient to determine the transition between laminar and turbulent flow. That process also depends on fluid properties and the pipe diameter. Reynolds used these to define a non-dimensional parameter, which is called the Reynolds number, that can be used to characterize whether or not the flow is laminar or turbulent. The definition of the Reynolds number is shown here at the top of the slide, and you can see it includes the density, viscosity, velocity, and a length scale L. The length scale is different for different kinds of flows. For flow over a flat plate, it's the distance from the leading edge of the plate. For flow around an obstacle, it's the diameter of the obstacle. For internal flows, we use the hydraulic diameter, and so on like that, so different definitions for different kind of flows. The Reynolds number serves as a criterion that determines whether the flow is laminar or turbulent. The value of the Reynolds number at which the transition from laminar flow to turbulent flow takes place is different depending on the kind of flow. In external flows, for flow past a flow over a surface, transition occurs at a Reynolds number of 500,000. For flow around an obstacle, at a Reynolds number of 20,000. And for internal flows, when the Reynolds number based on the hydraulic diameter is greater than 2300, the flow becomes turbulent. Certain characteristics of turbulent flows are especially relevant for engineering and modeling purposes. One of these characteristics is that a turbulent flow contains a wide range of turbulent eddy sizes. This can be seen in the visualization at the bottom of the screen where smoke has been introduced into a turbulent jet. The smoke collects at the center of the turbulent eddies, which are also called structures in turbulent flows, and you can see in the picture that it's possible to identify both smaller and larger structures within the turbulent flow. The range of eddy sizes is important because the behavior of the largest scale eddies that are present in the flow is different from flow to flow, whereas below a certain size we expect that the behavior of the smaller eddies should be more universal in nature. Another important characteristic of turbulent flows is that the fluid motion is unsteady, three-dimensional, and irregular, and the quantities that are transported in the flow, so this could be mass, momentum, energy, species, whatever is being transported, these quantities fluctuate in time and space. And these fluctuations result in enhanced mixing, which is the critical item of interest for engineering applications. If you have a flow where fluctuations are observed, but those fluctuations don't produce this enhanced mixing, then that flow would not be considered to be a turbulent flow. And the last characteristic that we want to mention is that turbulent flows are unpredictable in detail, which means that there's a randomly fluctuating component that's superimposed on the regular flow behavior. In many cases, we may be able to predict the regular flow behavior with different levels of accuracy, but the randomly fluctuating component is not possible to predict. Another important feature of turbulent flows is the energy cascade, which is depicted graphically on the slide. What happens in a turbulent flow is that the largest scale eddies receive their energy from the mean flow, and most of the turbulent energy is contained within these large scale eddies. As the flow evolves and the eddies stretch and interact, the energy is transferred to smaller and smaller and smaller eddies until finally, in the very smallest identifiable scales of turbulent motion, this energy is converted to internal energy by viscous dissipation. The theory of the energy cascade was developed by Richardson on Kolmogorov, and the scales where the dissipation occurs are known as the Kolmogorov scales.